Okay, I think we can get started. Let me introduce um, our guest speaker today, and we have very glad to have Tyler Peterson from Vizient to come to talk about MLOps to us. And Tyler is Associate Vice President on data operation at Vizient. And in this role is responsible for setting Vizient's data strategy and leading data product development. And his professional interest lies at the intersection of emerging technology and healthcare performance improvement with the emphasis on AI. And Tyler holds a Master of Health Administration degree from University of Iowa and a Master in Data Science from Indiana University. And Tyler is also a mentor for some of our students in a data AI data challenge. And thank you for being here and giving the guest lecture.
My pleasure. Thanks for the intro, and thank you everybody for having me today. All right, with that, we'll go ahead and dive in. So my background is, I'd say I'm rooted in analytics. I'm really interested in the healthcare domain. I've worked in healthcare basically since I finished undergrad in 2010, and it's a fascinating domain to work in. I'm not going to be talking about healthcare data or healthcare related machine learning all that much today. I'd actually like to focus on machine learning operations, or MLOps. In my career, I've always found myself drawn more to building systems as opposed to building one thing that does one thing really, really well. Early on in my career, I had an opportunity to work directly with health systems and our consultants to identify specific insights around specific service lines or patient populations. And while it's interesting to find interesting insights and pass those along to folks to do something productive, I've always enjoyed building systems that can make the overall process of analytics better, which I draw that as an analogous comparison to MLOps. Oftentimes when, at least speaking of myself, when I was doing my master's in data science, I was really interested in the model development process. How do I create a really great model that can infer and predict these things really successfully? But once I got into the mode of actually having to put machine learning into production, I became fascinated with MLOps, which is the craft of putting a process around machine learning such that all of the machine learning efforts developed by data scientists aren't in vain. You want to be able to produce a meaningful model that has as much impact as possible, and the way to do that is through MLOps. So with that, I'm going to start walking through my slides here. I can't see the chat, but if there are any questions that come up along the way, feel free to stop me. This can be very informal. So here's how we're going to structure our talk today. So first I'll talk about what's machine learning like without the ops. And then I'll get into the background of what is the lineage of the term MLOps. And finally, walk through what I think are some of the best practices in performing MLOps successfully. So a typical workflow when performing machine learning without the operational component it looks something like this. You work with your business stakeholders to define the problem, you collect the data and prepare it to the point where it's ready to be funneled through your algorithm to start training that model. And you develop your model, you fine-tune your hyperparameters, you validate it in whatever way you want to do it, and then you're done, right? You have a trained model, you have a classifier that does something. And you find yourself in a position like this. You have a Jupyter notebook where as long as you run every single cell in this exact order, it's going to work. But how do you get your model actually out of your notebook? maybe you even go a step further to save it as a pickle file or somewhere, but then like, what do you do with that? And the consequence of this is just performing academic insights. You have a model that can predict, but it doesn't really do anything, and it can't be used efficiently by anybody. And a data scientist can quickly find themselves in a perpetual state of developing proof of concept models with nothing meaningful to do. And maybe you do actually publish a model. Maybe you hide it behind an API and you integrate it into an application, but taking that model as is and then having it run in inference mode in an application in perpetuity is a recipe for some problems. Your data will likely evolve over time, whatever data is being prepared and run through the model in inference mode. The model performance will probably fluctuate over time, and if the underlying data shifts enough, performance will almost certainly degrade. When running applications in productions, it's not uncommon to have volatile or slow latency application performance. That's something you want to stay ahead of. And of course, reproducibility of machine learning work is something that is often called upon. Folks want to know, like, where did this data come from? How did you train the model? Why did you choose this model? If all of that is not maintained over time and all you have is a pickle file that you handed off to your product software engineers, you won't be prepared to answer those questions. So the consequence of all this is potentially degrading application and model performance with very little visibility into the root causes. You won't be able to reproduce how you even came up with that model in the first place. And anytime you do want to improve upon that model, you pretty much have to start over and not really, and start over without any sense of like why what you produced initially isn't working so well anymore. So now let's move into talking about what is the origin of MLOps. And it's rooted in DevOps and CI/CD principles. So DevOps stands for development operations. And I like to think of this as more of a state of mind than a specific tool or application. It's an organizational mindset that brings software engineers and data scientists and quality engineers together working collaboratively on the same code stack and the same environment. And more in a different way to think about it, it avoids the problem of, well, it worked on my machine, I don't know why you can't run my code. CI/CD, or continuous integration and continuous delivery, that is the actual process of executing that DevOps culture. So CI, or continuous integration, that is the process of automating how code is managed, unit tests written around that code, how productions are built and compiled, having clear delineation between development environments, staging environments, and production environments. And then continuous delivery is the process and how all of the code and changes move between those different steps. You want to make sure that code that's being developed in a test environment only moves up to the stage environment when it's appropriate. But you also want to make sure that when it's time, it's really easy to do that. Same thing with the process of moving code from a stage environment up to the production environment. And like I said, CI/CD is the mechanism that makes that DevOps culture happen. So extending off of that, MLOps it builds and expands upon DevOps in ways that are specific to machine learning workflows. So all the same stuff I just talked about, code version control, finally understanding and maintaining information on compute environments that were used, CI/CD, monitoring of performance. MLOps has all of that. And when I say monitoring performance, I mean system latency. MLOps expands upon DevOps by focusing very closely on data provenance, data set management, model training and registration, model performance metrics, and workflow management. And I'm going to talk through each one of those items. All right, let's get into some MLOps best practices by going into each one of those components. So data provenance and the consequences of ignoring that. Well, I'll first start off by loosely defining what data provenance is. It's an understanding of the source system of each data element that you're using in your machine learning process. And it's an understanding of the collection method for each one of those data elements. I don't know about all of you, but when I first started tinkering around with machine learning as an area of study, I was on Kaggle, downloading data sets and just reading into notebooks about what other people did with those data sets and coming up with my own experiments. But I never really thought that much about how those data sets came to be. The real world, of course, you don't get that luxury. Understanding very clearly where the data came from, who created it, why, how, all of those things are extremely important. As you're working with business leaders, the question of where the data came from is going to be one of the first questions you get. As model performance changes over time, understanding where the data came from is going to be really helpful when it comes to troubleshooting. If you observe feature drift or just shifts in how features are being represented in aggregate in your data set, understanding where the data is originally sourced from is going to be really helpful in diagnosing that. And then, very importantly, depending on the industry that you're interested in, there are regulatory and ethical requirements that go into explaining and documenting where all of the data comes from before it makes it into your machine learning workflow. So doing all of the upfront work to maintain that metadata is critical. And here's what you can do about it. You need to obsess over data element metadata. It's not the fun part of the machine learning data scientist practitioner's role, but it's something that will come back to haunt us if we don't focus on it. So we need to be very intentional about capturing the who, what, where, when, why of our data. And also focus on the documenting the context from different vantage points. What is the who, what, where, and so on for the business folks, for the technology folks, the domain experts, and data governance, of course. If in healthcare, we work with lots of sensitive, personally identifiable information, it's very important that we are clear about who is able to access what, because we don't want to, that's something that we have to, it's very sensitive and it's something that we have to protect by only allowing authorized individuals to access that data. And if we're not capturing that metadata in the course of our data provenance activities, we won't know who is accessing what. So next, data management. When I say data set management, I mean the sequence of events that lead from data set collection all the way to training data set creation. This is the aggregation and concatenation of everything that goes into getting you that nice, clean, tabular data set where you're going to be able to identify your independent variables and your dependent variables, as well as the feature engineering processes you have on top of the data. How are you encoding your categorical variables? How are you transforming numeric variables? How are you creating new features based on the original features that you're given? Third, the feature level understanding of your data. You need to understand what is the distribution of a given continuous variable. And you want to capture attributes about that distribution so that in the future you can observe any shifts that happen within those features. Same thing goes for categorical features. And finally, even though it might sound over the top, you want to archive every single data set that is used to train a model that you end up using. Because if you are asked inevitably to demonstrate that you can reproduce that model, you know that you're going to need that data set. So that needs to be preserved as is. The consequences of ignoring this is you won't be able to explain the data elements and the features at a data level. You won't be able to detect features when they drift from original distributions of when you train the model, and you won't be able to recreate what you did in the first place. So in order to address this, like I said, you need to archive every single data set that is used when training a model. You also want to exercise version control of the code that is used to create, transform, whatever it is that you're doing to your data set to get it to the point where it's ready for fitting. And you also want to constantly monitor each feature for changes. So whether it's a continuous variable or a categorical variable, as you get new data in, when this model is running in inference mode, you want to continue to accumulate that and observe the distributions of the individual features within your data set to make sure that your model still represents the data as it's appearing in its current state. So next, moving on to model training. I think this has two prongs. This is the compute environment and the code that you use to actually do the model training, as well as the process for training your model and validating its performance. Everything from algorithm selection to hyperparameter tuning methods, how you set your random number seeds, and so on. And if you don't capture this in the process, you'll have an inability to explain how you train the model and why a particular model was chosen. And of course, you won't be able to reproduce the model either. In order to address that, it requires meticulous tracking of experiments. Basically, you want to understand everything that you tried, whether it worked, whether it failed, the different algorithms you chose, the loss functions you used, the loss values that you accumulated along the training process, the performance metrics that were used and the values associated with those, your hyperparameters that you evaluated, your hyperparameter search methods, whether it was random selection, grid search, something fancier like Optuna or HyperOpt or whatever Bayesian optimization algorithms are out there today. All of those things need to be cataloged and maintained. And of course, you also want to be able to describe what kind of compute environment you used. If you're using Python, you should have a virtual environment where you can document which version of Python you use, different packages and the version numbers associated with those. And finally, the actual code that was used to make the process go. Moving on to model registration. So this is a registry is something that maintains all of the information for all of the models being used at every single level of development and production. You can think of it as a marketplace for models that are going to be consumed by other applications. If you have, let's say, 10 different products that are being infused with machine learning models, let's say 100 different models are running in production at any given time, you want to be able to demonstrate where those 100 models appear across those 10 different products. And a model registry is a great way to do that. Without one, you won't have clarity into which models are being used where and for what purpose. And then, as any machine learning operations workflow should have, not only do you have production models, but you also have experimental models that might just be running in the background. They aren't doing the actual inference in the application, but they're candidate models. They're being run sort of in the background, just in case, as an experiment. Maybe you want to see if doing this feature engineering method is better than whatever the production model is doing at that moment. Having a model registry allows you to delineate what are your production active models versus those that are candidate experimental models. And another key benefit of having a model registry is integration with the products themselves. It's as the whole CI/CD process works around the overall application, the machine learning model is just another file. It's just another artifact that can be picked up by the application and integrated into the production environment. Having that registry makes it really easy for other applications to just go out there and grab the model and use it. This one's pretty straightforward. There are lots of different products out there for managing model registries. I like to think of it as like shopping on Amazon on your phone. Like I can look for any given product and I can evaluate different attributes about it. I can see how it's performing. I can see reviews. I need to have all of that metadata at my fingertips in order for me to be able to understand, is this the right model for my use case? Performance metrics. So this is, I think in a way, pretty straightforward, at least on the surface. You want to understand how effective is your model as it's running in its current context. But beyond that, you also need to understand the latency involved with that system. Is it generating predictions in the application where it is as quickly as it should be? And is that consistent over time? And finally, we shouldn't assume that a model trained once is going to be the model that lives there forever. So having triggers in place for determining when to retrain a model is really helpful. If these things aren't in place, there won't be visibility into models that are deteriorating while in production. You also won't have clarity into when to replace a production model with a candidate model, and you won't have visibility into a model that is running slowly for whatever reason in production. So in order to address this, continuously tracking model accuracy for every single model that's running in inference mode in production is critical. And there needs to be decision thresholds set at which once performance degrades to a certain point, like red lights need to flash and that needs to be addressed immediately. I also find it helpful to set triggers to automatically set off a retraining process. Maybe you have a model where you just want to retrain it every single day at this time, and that's perfectly fine. You might have another metric-based trigger where if the accuracy falls below, let's just say 90%, you want that model to be retrained. Event-based is a little bit more ambiguous, but if there's a dependency within the application that sees a big change of some sort and you always want the model to just be retrained there just for safe measure, that would be an event-based trigger. And lastly, continuously tracking latency associated with inference and setting a threshold of how many, let's say, milliseconds are acceptable for every single inference that's performed. And lastly, workflow management. So I think this is just a wraparound of everything that I've been discussing. This is the end-to-end management of everything that goes into machine learning operations practices, everything from data provenance, understanding where your data came from, to enabling the automated production deployment and monitoring of models in production. And like I keep saying over and over again, if you ignore this, there will be confusion, inefficiency, and poor performance. My suggestion on how to approach this is any good data scientist needs to become best working friends with their product development and software engineering counterparts. It will ensure two things, in my opinion: that you have more time to focus on the data science efforts that you enjoy most, and it will make sure that the fruits of your labors are as good as they should be. If not, it's the data scientist finds themselves handing off models and just, kind of waving by and hoping things work out well for that model once it hits production. And usually things don't go that smoothly. Aside from the people portion of things, there are lots and lots of tools out there these days that help put the right confines around people to do MLOps activities successfully. if you're working in the cloud environment, AWS SageMaker, Azure, ML Studio, or whatever they call it these days. GCP certainly has its own, with lots of other non-major tech cloud companies, lots of other applications out there too that make this kind of work not just seamless, but actually pretty fun, in my opinion, to be able to manage this machine learning work this cleanly. All right, and with that, I would be happy to answer any questions.
Thanks, Tyler. This is awesome. It was fascinating. This type of things were not covered in most of our courses. Maybe they should. For sure, I kind of really enjoyed this the overview